Right. Now a little bit more complicated question. Be something like this. So Saturn, well, first the sun's mass is 1.99 times 10 to the 30th kilograms. Saturn is 9.024 AUs from the sun at aphelion, or sorry, at perihelion, and 10.09 AUs from the sun at aphelion. The mass of Saturn is 5.68 times 10 to the 26th kilograms. Times 10 to the 26th kilograms. What is the magnitude of Saturn's change in potential energy from perihelion to aphelion? Now this is, again, pretty straightforward, but the numbers plugged in are pretty complicated because we've got to find energy at two different points. So a change in potential energy would be the potential energy at one point, G M1, M2 over R1 minus negative, so plus G M1, M2 over the other distance. Now notice you can factor that out. Minus GM1, M2, and get 1 over R1 minus 1 over R2. This is a little bit easier to plug into your calculator if you do it in this format. And then now we can plug in numbers. We've got the mass of the sun, the mass of Saturn. I like to combine the powers of 10, so sun is 10 to the 30th, Saturn is 10 to the 26th. Put those together, you've got 10 to the 56th. Then we've got times 1 over R1, which is at perihelion 9.024 AUs. In case you didn't remember, 1 AU is 1.5 times 10 to the 11th meters. You don't need to memorize that. If I give you anything in AUs, I'll give you the conversion on the test or quiz. There is no quiz on the test. Minus 1 over 10.09 times 1.5 times 10 to the 11th. So that's how we would go about finding that. And then plugging those numbers into the calculator gets you a difference of about, since I said magnitude, we don't need to worry about the sign or the order we subtract in. 5 point, how many sig figs? I think 3 sig figs, 5.88 times 10 to the 33rd joules. Note that if I asked for the magnitude of the change in kinetic energy, it would be exactly the same answer because change in kinetic energy is equal to change in potential energy when we are only dealing with conservative forces. All right. Let's take a look at another sample problem we could do. Now we're going to get into conservation of energy problems. These last couple have been just about potential energy, but let's look at just a couple that are about both conservation, about conserving the total mechanical energy. Sorry. So, say for example, Pluto's average distance from the sun is 5.874 times 10 to the 12th meters. At this distance, its speed is 4.7 kilometers per second. What is its speed at perihelion, which is 4.437 times 10 to the 12th meters from the sun? Okay, well, we know the distance and speed at one point in the orbit, so we can figure out the distance and speed at another point by applying conservation of energy. We know in a situation where energy is conserved, we can say potential energy plus kinetic initial is equal to potential energy plus kinetic energy final. In this case, what's going on? Well, our initial potential energy is going to be minus G mass 1, which is the mass of Pluto. What is the mass of Pluto? I don't know, so I'll just put mass of Pluto times mass of the sun, which we can borrow from the previous problem, 1.99 times 10 to the 30th. Now you could look up Pluto's mass if you wanted to, but stay tuned. And initially, we've got 5.874 times 10 to the 12th for our distance. And don't forget kinetic energy is just 1/2 mass of Pluto. V squared, 4.7 kilometers per second is 4,700 meters per second, equals final potential energy, which is minus G mass of Pluto mass of sun over R squared, which is 4.437 times 10 to the 12th plus 1/2 mass of Pluto. The final squared, I just barely had space to fit that on the line. And what do we notice? Look at that. Mass of Pluto is in every term, so we can get rid of it. So we don't need the mass of Pluto to actually solve this problem. And from that point on, we can go ahead and calculate. And when you plug all this into your calculator, you get that the speed is about 6.060 times 10 to the 3rd meters per second. So with sig figs, 4.1 kilometers, so that's about 6.1 times 10 to the 3rd, which is 6.1 kilometers per second. So that's how we deal with that full-blown sort of conservation of energy problem. You write minus gm1 m2 over r plus 1/2 mv squared equals gm1 m2 over r plus 1/2 mv squared. Okay. Now, another thing that comes out of the idea of energy conservation is what's called escape velocity. I referenced this when we mentioned black holes. Remember, black holes were defined by escape velocity being greater than the speed of light. But escape velocity, I said, is the speed needed for an object to escape the gravitational pull of another object, a planet, a much larger object typically, but a planet or a moon or whatever. Now, there is no point where two objects will exert zero gravitational force on each other, so to escape means it won't fall back down to the planet. And what that amounts to, the limit where that can happen, is if it had a speed of 0 meters per second at an infinite distance away from the planet or moon or whatever object it is. So what that amounts to is that your initial energy initial energy minus g, and I'll use little m, big M. M is the object that's escaping, big M is the gravitational, the mass of the object it's trying to escape the gravitational influence of. So its initial energy has to be equal to, well, it needs to get out to an infinite distance away, which makes this potential energy 0. It needs to just barely do it, which means its velocity is 0 there. So so that means a total of 0 mechanical energy. And so this gives us a formula for the velocity an object needs to have to escape. What this amounts to physically, for example, in the case of the Earth, this is the speed at which you need to fire an object out of a cannon or a big gun or something for it to escape Earth's gravity well from the surface of the Earth, if you plug in radius of Earth. So we can do things with this formula. For example, I can ask you to find the escape velocity of the moon. And then I'd have to tell you the mass of the moon is about 7.35 times 10 to the 22nd kilograms. The radius of the moon is 1.74 times 10 to the 6 meters. And then we can plug it in and figure it out. Escape velocity is root 2 gm over r, which is square root 2g 7.35 times 10 to the 22nd over 1.74 times 10 to the 6th. Then we can plug that in to the calculator to get our answer. And I forgot to press square root, so I'll have to do that at the end. Oops, I don't want cosine, I wanted parentheses. Square root of that, and we get 2.37 times 10 to the third. We do have 3 sig figs, so 2.37 times 10 to the third would be 2370 meters per second is the escape velocity of the moon. I do want to note this that a little bit earlier I just briefly mentioned the formula. This formula, came out of a different situation. This is the speed of a circular orbit with radius r. So the formulas look similar, which makes sense. They're both velocities, so they should be dimensionally the same, and they are. Gm over r. 2 doesn't have dimensions. But just keep in mind, this is speed of a circular orbit. This is, the speed you'd need to escape, to make it out.